Alright, so the last two examples, this is another example of a chain rule and a logarithm, and then I'm going to get to an example where I'm actually going to plug in and find my slopes, my rate of change. Alright, so example 8 first. Alright, so this does involve the chain rule because it's the natural log of the function x squared plus y. So it's actually the natural log of the unit circle. Alright, so first with respect to x, so the derivative with respect to x, well the outside function is the natural log. The derivative of the natural log is 1 over whatever's inside. That's 1 over x squared plus y times the derivative of what's inside. Now it matters which variable I'm looking at. I'm looking at the x variable. Right? So there's only one x term inside. It's the x squared. That's what's changing. Y squared doesn't change, so it zeroes out. And so it's going to be times 2x if I write it as a single fraction. Alright, well this derivative with respect to y is not much different. Right? Chain rule actually isn't too bad because the first part's exactly the same. Right? The derivative of the natural log is 1 over what's ever inside. Times the derivative of what's inside. Well now, instead of looking at the x part, we look at the y part. Right? So the x squared zeroes out, because there's no y. I take the derivative of y squared, which is 2y. And so again, there's a subtle difference in this one. They are different, right? 2x divided by my unit circle is different than 2y divided by my unit circle. And so that would be my rate of change functions, my first order partial derivatives. Alright, the last one, which again didn't quite copy over, I wanted to find the derivative at a specific point, negative 4, 1, and compare. Alright, so I want to find the derivative of this function with respect to both variables at a given moment. Alright, so at the specific point where x is negative 4 and y is positive 1. Alright, and we'll kind of interpret it too. Alright, so first with respect to x. So the derivative with respect to x is going to give me a 12x squared minus 10y. That zeroes out. Alright, then I'll plug my point in, negative 4, 1. So I get 12 times negative 4 squared minus 10 times 1. And this is going to come out fairly large because it's 12 times 16 minus 10. Double check that. 182. Alright, so 182. And so this means at the point negative 4, 1. Alright? So in this case, it's the negative 4 that I'm looking at the change in negative. So if I'm near negative 4, negative 4.1, negative 4, negative 3.99 or something along those lines. The function is increasing at a rate of 182 units, whatever. So if this represented profit, profit would be increasing by 182 units as x changes. Alright, so x would represent some type of variable in terms of profit. So it would be some type of, maybe it's capital and labor. X would represent capital. So if I increase capital, alright, my function would increase by 182 units at that moment. Alright, well, how does the y variable affect it? Does it affect it differently? How differently does it affect it? Alright, so now we'll look in the y direction. Alright, so take the derivative now with respect to y. So f sub y. Okay, go back up here and look at my y. So those are the two parts that are y, so negative 10x, negative 10x plus 8y cubed. Alright, and then I plug this in. So again, that would be all my rates of change. We wanted the one at x is negative 4, y is 1. So I get negative 10 times negative 4 plus 8 times 1 cubed. And so that would be 48, right? So I get 40 and then 8. And so this one is different, right? That's a big change. The first one's increased, they're both increasing, but the first one's increasing a lot faster. 182 units is a bigger increase than 48 units. They're both increasing though. Alright, at the moment, negative 4, 1, the function is increasing by 48 units per change in y. And so y had less of effect on it, right? Y did not affect, so if this were profit, profit, I would rather change, if I could only change one variable, I'd rather change x, right? Because x is going to give me more profit. For cost, right, the change in y is the way I'd want to go because the cost was a lot less. The change in cost would have been a lot less if I changed y than when I changed x. So again, it would matter what the function is, but which variable I changed did affect my outcome a lot differently, right? When I changed x at that moment, I had a bigger increase than when I changed y. All right, and so that's our partial derivative. So that's the first part of 6.2. We'll stop there.